Hi, I'm Yichi Zhang from the Slide Lab at the University of Michigan. I'm glad to introduce our work, DANLI, Deliberative Agent for Following Natural Language Instructions. The problem we are looking at is to model an embodied agent in a 3D virtual environment to complete common household tasks given by a human commander through dialogue, such as preparing food, cleaning deep dishes, or rearranging items. In particular, we mainly focus on the execution from dialogue history setup in Teach. In each session, the agent is given a situation in the middle of a task, where the task context consists of the task-oriented dialogue history, the previous observations, and actions taken by the agent. The agent needs to figure out the task goal and the steps needed to complete that goal. During evaluation, the agent will be placed in an interactive simulated environment, where it performs actions and receives visual observations until the task is believed to be completed. The performance will be measured by the final task success rate and the efficiency in terms of the number of steps. This problem is extremely challenging in 3 aspects. First, understanding the task goal and the situation requires reasoning over multiple modalities. Secondly, the agent can only perceive the world with its egocentric vision of RGB image, which means the state is both partially observable and high-dimensional. Thirdly, tasks may be long horizon and composed of multiple subtasks. Existing works in embodied AI research mainly focus on modeling the agent in a reactive manner, where the agent learns to imitate behaviors encountered in the training data and make reactive decisions solely based on the current situation. As a result, such reactive agents are not sufficient to solve complex tasks like the ones in the Teach benchmark, as evidenced by their low task success rate. In addition, these solutions often suffer from low efficiency since the agent does not explicitly reason over the state space for finding an optimal solution. This motivates us to build the agent in a deliberative manner, where the agent does not make short-sighted decisions, but proactively plans ahead to search for the most efficient solution to solve the problem. To support planning, deliberative agent must maintain an internal state for tracking the current progress and the environment, and be able to perform symbolic reasoning over the state. Besides task performance, symbolic representations also provide a better interpretability and transparency of the agent's decision process, which greatly benefit human-AI collaboration and also for developers to better understand the capability of the agent. However, although such agents have shown promising performance in simpler environments, they have not been much developed, much explored in embodied AI research, given the complexity of connecting natural language and vision to symbolic representations. In this work, we introduced DANLI to bridge this gap with 3 main contributions. First, we propose a neural subgoal predictor to predict symbolic subgoals from situated dialogue history. Secondly, we propose a spatial symbolic word representation to track and ground objects, which can facilitate both path and task planning. Thirdly, we propose an online symbolic planner, which can generate efficient and interpretable plans, and an exception handling mechanism to help the agent recover from errors. Here is an overview of DANLI's architecture. In our design, we take advantage from both the recent advance of neural models in processing fuzzy language and image data, and the interpretable symbolic reasoning process empowered by classical PDL planning. Next, we will introduce how DANLI works. As shown in the upper part, DANLI will first predict a set of symbolic subgoals from the task context before making any movement. To achieve this, we leverage a pre-trained BART model to encode the interaction history, including both the dialogue and both actions. The symbolic subgoals are decoded sequentially in an autoregressive manner. We found in our experiment that first predict what has been completed so far can benefit the prediction of future subgoals, because the model may have a better idea about the progress. Please see the paper for more details. Then the agent begins to roll out in the environment to complete all the predicted subgoals. At each step, the agent first updates its internal representation from the latest observation, then checks the task progress in the subgoal monitor. Finally, use a PDDL planner to generate the plan for the current subgoal and execute a planned action. To learn the internal representation from egocentric vision observation, DANLI first leverages a panoptic segmentation model to recognize the object instances, and a depth estimation model to get the depth information. Then a 2D to 3D projection operation is used to transform 2D detections into the 3D voxel map. The map is updated across the entire session, which can be served as the agent's memory about the world. Furthermore, we propose a state estimator to estimate the physical state of objects, as shown in the pop-up boxes in the right figure. Since all the objects and predicates are grounded on the voxel map, we call it a spatial symbolic representation, which can be used for both task planning and task planning. After the representation is updated, it goes into the symbolic planning pipeline to generate plans. The subgoal monitor first checks about whether the current subgoal is completed, and if so, it moves on to the next subgoal. Together with the current world state induced from the internal representation, the PDDL planner outputs a sequence of actions that can transform the current state into the goal state. If a navigation is planned, the path planner will be invoked to plan for the shortest path based on the map. As the perceptions can be noisy, the agent may encounter unexpected exceptions or mistakes from time to time. How to recover from such mistakes becomes an important issue to improve the task performance. Thanks to the interpretability of DANLI's symbolic reasoning process, we propose a decision tree-based exception handling mechanism to help on this. Please refer to the paper for more details.
Our deliberative agent is one that is both effective and efficient. Here is a quick overview of our results. On the left, we are seeing success rate, which measures the proportion of successfully completed tasks. We can see our deliberative agent substantially outperforms reactive solutions and achieves a new state-of-the-art performance in both seen and unseen environments. On the right, we are seeing path length weighted success rate, which factors in efficiency when measuring success rate. Under this metric, our deliberative agent doubles the performance of reactive agents in seen and unseen environments. Here is a breakdown of trajectory length of our deliberative agent, which is shown in blue, compared to the trajectory length of a reactive agent, which is shown in yellow. The horizontal axis is the relative length taken by each agent. The vertical red line indicates the length taken by human. We can see on average, our deliberative agent takes shorter and closer to human trajectory length than reactive agent, indicating deliberative agent produces more efficient plans. Deliberative planning also allows interpretable exception handling. With our symbolic word representation in a planner, the agent can know exactly why an exception has happened and thus attempts to auto-recover from it. To demonstrate this interpretability, we plot the exceptions encountered and auto-resolved by DANLI. Each horizontal bar is one type of exception. The total length of the bar indicates how many exceptions there are under that type. And then the green portion shows how many incidents of that exception type are auto-resolved by the agent. We can see that DANLI is able to auto-recover under many types of exceptions. Even when DANLI fails to auto-recover from exceptions, Its fully interpretable deliberative reasoning process provides clear intuition about why, which helps developers diagnose and improve the system continually. To demonstrate the interpretability of our deliberative agent, we build an interface to visualize its internal states during execution. With this interface, we can see all of the agent's internal thought process, ranging from 2D object detection, 3D map construction, all the way to sub-goal prediction and action planning. This enables developers to quickly diagnose errors and continually improve our system. Let's see this in action. Here, the agent is given a half-completed interaction and dialogue history about making coffee, and now the interaction is being replayed. As we can see, DANLI uses the interactions to construct a word representation. And now, the agent goes into rollout stage and starts predicting sub-goals and action plans to complete the task. And finally, the agent successfully completes the task of making coffee. To sum up, our deliberative agent DANLI uses a neural subgoal predictor to process fuzzy dialogue and visual input and predict the subgoal. It constructs a spatial symbolic word representation which helps track and ground objects in a 3D voxel map to facilitate both path and task planning. And finally, it takes advantage of a symbolic planner to generate efficient, interpretable plans while allowing online exception handling. That's all about DANLI for now. For more details, please check out our paper. Thank you for your attention.